Hello, everyone. Welcome to the webinar today. Like Kareen said, my name is Trisha West. My background is actually in aerospace engineering. I am a total space nerd through and through. I actually used to do a little bit of R&D for some internal satellite stuff with the US Navy. Nothing crazy. It was all just kind of generic communication satellites. And then switched over to RAN 3D. I've been here for about 8.5 years, providing some Creo and then CATIA V5 classes. And now that a lot of our customers are kind of transitioning into 3D experience, teaching a little bit of those classes as well. So let's go ahead and jump into today's webinar topic. And I want to start off by talking about that term, simulation in CATIA. It can, kind of cover a whole host of sins. And typically, when I have discussions with my students and I say that word simulation, they assume that, what they need is kinematics. So kinematics is granted with the KIN license, the KIN license. Now that, you can do a simulation with the kinematics, but it simulates more of what I would like to call kind of the intended motion of the assembly. So you could simulate like a car door like rotating open. You could simulate, an engine. So you can make kind of the piston move up and down, and then that will kind of drive the rotational change of the crankshaft and etc. So I'm going to show you a video here in just a second, and what you're going to see in this video is a kinematic scenario. So we will have a rotational movement kind of driving this entire simulation of other parts. And these parts are connected together through these mechanisms. So basically what we're going to have here are different joints. And those joints define, again, the intended motion of the assembly. So let me come over here and hit play, and we'll see the rotation of my blue piece rotates the yellow, rotates the purple. The purple kind of slides the green bar. If I play that again here, and then maybe those are connected so that way if the green bar is sliding, the blue bar is sliding. So again, this intended motion of the assembly, that's what you generate in a simulation file with that different license called the kinematic license. And that's not really the purpose of obviously our webinar. I just wanted to clarify that because there is differences between the two, and like most people, as soon as I say simulation, say, oh yeah, well I've got the kinematic license. That's not what you need when you're doing something like trying to simulate the assembly or disassembly of a component within an assembly. In that, you are going to need the DMU fitting simulator, which is via the FIT license. And again, that's what's responsible for creating that simulation of an assembly or disassembly. So here I have a little video clip of, in this case, it's a disassembly file, right? So I've just got a little fastener that needs to come out. Now notice what that fastener is doing. He's not coming straight up through an obstacle that he knows he can't pass through. He's kind of working around it. So that's the whole purpose of our webinar today, is to kind of show you a quick way to simulate this. And that leads us to like, what can you do exactly with CATIA's fitting simulation? So let's say that you are tasked with maybe it's a rework feasibility study because you've had something to go wrong and you've got a massive recall on something. So you need to be able to see how easily something is able to be removed or disassembled from like an assembly. So the fitting simulator is going to allow you to visualize this information, and it does a pretty good job of visualizing that for you on the screen. So what you'll do is you'll develop a track, or a track is basically just the path that it should take. And it's the path that it should take in physical space. Now, along with that, you can perform clash analyses. And just like you saw on my previous slide, you can create these little simulation scenario files. So that way, if you're, needing to present on this topic and you want to include a video like you saw on my last slide, you can do that as well. So these tools are going to allow you to help validate the initial production assembly, but also help address serviceability and any type of like maintainability. So if you've got like yearly maintenance that you've got to do, and again, you want to make sure that you can easily take something off and on, something like that. So the focus of our webinar today are going to be these 3 little bullet points here. We're going to perform path analyses to really derive the optimum assembly or disassembly path that the object should take. And then as it's moving along that path, we're going to monitor certain measurements perhaps, so that way we can confirm that we have minimum clearance distances that are being maintained. And then the last thing that I want to show you, which is kind of a cool little visual trick, is to create a swept volume, which if you've done kinematics at all, you can also do swept volumes in there as well. All right, so I don't want this webinar to be like 4 hours long. So I'm going to be assuming that, you know, certain things like making a track, sequences, shuttles, detecting clash, those are already known to you guys at least a little bit. Now, I am still going to touch on these things here in the webinar, but like I'm not going to go through every single option of every single thing in the dialog box because, again, trying to keep this under an hour. However, if you would like to see more details on all of these topics, I have already created a couple of video tutorials for these, and I just really quickly want to show you guys how to access these in our blog. So you would go to our blog here, resources.ran3d.com, insights from within, and in this top corner here where it says to search for, search in the resources, just type in something like fitting. So pretty much all of the previous videos that I've done, I've always titled them, so that way they'll kind of get flagged here with the fitting simulator. So just type in fitting and hit search, and that is going to return the following results. And I've placed kind of my recommended watching order over here to the right side. So the first thing that I would recommend for you guys to read is the blog Applying Motion Using Fitting Simulation. And that's going to cover how to make a track and like all the ins and outs of track creation. Remember, tracks are just the path that you want to have the object to take. Then I would have you to watch the creating a sequence. Then you would adjust the motion duration. You can also do that inside of a sequence. So that's the third thing that I would have you all to watch. And then finally, the kind of the longer video here is detecting clash in CATIA version 5, fitting simulator workbench. So clash, of course, in CATIA simply means an interference. I always like to tell my students that CATIA can make us magicians because in reality, I can't take a solid object and make it fly through another solid object, but I can in the virtual environment of CATIA. So anytime you are creating any assembly file, it's really important for you to always check to see if you have clash, especially if you're making a path, like you're manually building a path. Because chances are, like if you just do the eyeball and you're like, oh, I don't think it clashes, you could actually have a very minute clash that you're just not seeing with the human eye. So detecting that clash is going to be a big thing. So that leads us to the bread and butter of this webinar here, which is, you know, there's got to be an easier way than for a designer to kind of meticulously develop a path and figure out all the spots that it's clashing and kind of work around it. So that is where the Path Finder comes into play. So this is kind of our major button here for this webinar. So the Path Finder tool is going to eliminate clash conditions between the object that you're moving and any surrounding components in the assembly. So with this tool, we don't have to worry about there being a clash created along the path. Now, it does require the use of an existing track. So you will have to make one initially, But you can make it rather quickly because it only needs two spots. It needs where it should start from and where it should end up at. So you really only have to give it those two data points. Again, the initial track should be pretty quick to make it. So let's look at the example below here with our little door handle. On the bottom left picture, you can see that they're wanting to show the bolt just being removed. So they made an initial track, disassembly track, and they kept it really simple. It's a linear track that moves upward. But clearly, like it can't just go straight up because there's a door handle in the way. So that's going to clash. So the beauty of the Path Finder is that after it does its calculations, it'll modify your original track so that way it avoids those obstacles. And it'll, move it from start to end without interfering. And it does that while confining it to a specified volumetric space of your choosing. So if we look at the picture down here on the bottom right, you can see that what they did is they had the bolt to kind of come up, and then it worked its way around the door handle, and it kind of went over to the left-hand side, right? It swung around to the left. But now, if you would want to have a little bit more control and say, I'd rather kind of swing that over to the right, you can do that by adjusting the volumetric space that you are given. So let's step through kind of the process of filling out this Path Finder. So step number one, simply develop a track. Again, it needs a start and an end location. You can put a couple other points in the middle, but the important thing is you got to have the start and the end location, and that's it. Step number two, hit the button, select the track to be modified. As soon as you do this, you're going to see a yellow box around your environment. That yellow box is the bounding box. So that space that the yellow box creates is all of the potential locations that you're allowing the object to move to be able to find the path around the obstacles. So you probably want to do a little bit of due diligence here and not allow it as much space as the entire environment, as you can see here, because we don't want it to take time maybe bouncing over here at the corner. So, try and adjust this so that way you're giving it a smaller space. And you just adjust those by left clicking and dragging those faces. Now, sometimes seeing a 3D environment on a 2D computer screen leads to some optical illusions. So in you adjusting the bounding box, you might want to use your quick views. So maybe look at it from a side view and then drag that in, or a top view might make it a little bit easier. But again, you're going to readjust that bounding box. Now the rest of the dialog box that you're going to have to fill out here, there's kind of two tabs. There's a basic tab and then there's an advanced tab. So we're going to go through some of these options. I'm going to describe what they all do. And then I took a couple of pictures so that way we can kind of see it. And the reason why I took these pictures is because every time we run this, it takes a couple of minutes. So I'm not going to be showing you all of these options when we get into the actual demonstration, because every time I hit apply, we would have to kind of sit in awkward silence for like 3 minutes. So yesterday, I did all this and I just took screen captures so that way we can compare these. All right, so starting off with the basic tab, we have the visualization option. So CATIA is going to move the object, and every time it moves the object according to the step size, it creates a little data point, like a physical location where it moved it to. And it creates that data point as a little red X on the screen. So if you want CATIA to show all those little red X's, you want the visualization to be on. If you don't want CATIA to show those, turn it off. Or if you want CATIA to show only the every 20th calculated position, you would choose that Strombo option. Then you've got ignore collisions. So in this case, and this is really more beneficial for if your part that you're trying to move starts off in an initial clash condition, it'll ignore that initial clash that you might have between the object that you're moving and the environment. And then we have this area down here that's grayed out called the validation option. Now this option is going to display basically the orientation when you're using a shuttle as an object. So we can't modify these here. It reflects what the shuttle options are. Now, why would you want a shuttle? Okay, so controlling your path finder object with a shuttle is a great option when you don't want the thing that you're moving to kind of rotate, or I would call it wobble, throughout the path. So for instance, let's say that the object that you're moving maybe has fluid inside of it. And maybe there's like an opening somewhere, so that way, you know, if that thing that you're moving tips one way or the other too much, like I could potentially tip out some liquid. So if you have something like that, you might want to consider making your initial track from a shuttle, so that way you can control this vector angle limit. And I'm actually going to show you this when we get into the demonstration. So the last thing I got to show you in this basic tab is the step size. So the step size is what they call the translation size. So that's how much CATIA is kind of moving the object and then taking that data point. There's 4 options: small, medium, large, and advanced. So here I have 2 screen captures to show you. Again, these take several minutes to run. So I did all this yesterday and just took screen captures from the same spot so we can look at them. And I'm just using the medium and the large because when I tried the small step size yesterday, after 10 minutes, it hadn't even made it through like half of the maze. So you guys just have the medium and the large step size because I sometimes don't have a lot of patience. So the medium step size, as you can see, CATIA, told me it was about a 2.5 mil step size. Compared to the large step size, which is like 5 millimeters, you can see all those little red data points that I was talking about. So notice, that you get about double the data points in that medium area because, that translation step size is smaller. So the smaller the step size, the closer it should match the original path or track that you created. But, the downside there is that it takes longer to calculate. And again, I don't have a picture here of the small step size because it was just taking forever. The advanced option, so you'll have to pull down the little drop-down list here and choose advanced. But when you choose the advanced option, you then specify in the advanced tab over here where it says motion. So you'll actually specify this translation step size here. And again, that translation step size is that physical distance it moves the object when it's trying to find a new point along that path. So this is the same screen capture as the previous slide. So with the large step size, CATIA kind of assumed about a step size of 5 millimeters. And then with that custom step size, I manually entered 10, which is, double the size. So obviously that means if you look at the pictures, right, I have about half the number of those little data points. So it still creates the path, and the path is still going to be very similar. It's a larger step size in between. You also have this thing called a rotation gain. You take that number and multiply it by the translation step size, and that's basically how much that you can rotate the part. So we'll see this here in a second. As my little, I'm calling this a mouse. So as I move my little mouse through the mouse maze, it'll kind of rotate a little bit. So again, consider that, and if you don't want it to rotate that much, you might want to create it as a shuttle. All right, then we have some advanced options here. The first one is the smallest detail. It's the smallest entity the system considers part of the environment. Well, what does that mean exactly? So when the Pathfinder runs, it builds an environment of all the different possible locations that the object can be translated or moved to. So this option controls the smallest entity that it kind of considers part of that environment. So for example, if I had a hole, and that hole had a diameter size of 5, okay? But if I set my smallest detail to 10, right, that's larger, obviously, than the smallest detail. So if the value is larger than the diameter of the hole, then that technically that hole is not included in the environment, so the object isn't allowing itself to move into that space generated by the hole. So again, there's a trade-off. The smaller you make the value, the more computation time is needed. Then you've got your bounding box. Initially, it's going to show up around the entire environment. You could have it to start off by just being right around the path, or anytime you take those yellow surfaces and you drag it to a different location, it defaults to custom. So pretty much you're always going to have to kind of adjust it. So majority of the time you're using a custom bounding box. And the last option, it says if you only want the path finder to kind of find a path for part of the track, not all of it, then you can choose that option, but you do have to specify a start and an end point on the track. And the last thing that we have is something called the repulse effect. This one, I think, probably took the most amount of time for my little simulation to run. I think I was waiting about 10 minutes for this thing to chug along. So again, patience is definitely needed when you're doing these fitting simulator scenarios in CATIA. So I have some comparative pictures for us to take a look at here. The repulse effect by default is set to high, and the repulse effect just says, hey, when the object that's moving, when it senses a clash, it'll try and rebound or move away from that as best as possible quickly, versus a low repulse effect. And if you look at these pictures, you can see that, you know, it knows that it has to move around this little wall. So you can tell in the path that it kind of starts early trying to move around that wall. Whereas with my repulse effect set to low, it moves a little bit closer to that wall, and it stays closer to that wall as it moves around it. So you'll set all of these options, and then you're going to hit apply, and then you're going to maybe have a coffee break or a bathroom break, because again, sometimes it takes it a while. You'll actually see you'll see the object moving. You'll see kind of it bouncing around certain obstacles, figuring out the best path to take around it. But in the end, it should spit out a path around these obstacles. Now, the last step here, which is optional, is that you can take those paths and you can smooth them. Now, when you smooth them, you are going to specify once again a translation step size. So that's the size that it's moving it along that path. And the smaller the value, the longer it'll take to run, but the closer it'll stay to the original track that it created. And then here's kind of the downside to smoothing a path, is that by it smoothing the path, sometimes it will actually reintroduce a clash condition. So this is on you guys. You should always do your due diligence and play the track and make sure that you don't have any clash, and you can easily do that with the clash detection that you have on. All right, so I'm going to demonstrate a couple of these findings here with our Pathfinder, and we're going to do this by making a mouse move around this little maze that I've created. So let me jump into the CATIA software. Hopefully everyone can see my screen. Now, remember, the thing about CATIA is that all of the buttons can move. So where I like my buttons could be different from where you like your buttons. But the fitting simulator workbench is where we're going to. You need that FIT license. And then just to quickly show you, that's going to be underneath of the digital mockup category. So it's just right here, DMU fitting. Once you're inside of here, it's just really these two main toolbars. You've got DMU check and then the DMU simulation. So the goal is to have my little mouse to start, work his way around all these obstacles. So again, if you have a bracket, right, that you're trying to either assemble or disassemble kind of in like an awkward area where it's got obstacles, you want to make sure that you can get to that area and then maybe at the same time maintain a minimal clearance distance as it's getting there. So that's what we're simulating here by making our mouse go through this maze, ending up over here. So to get started, I'm just going to create an initial track. And again, see all those previous videos and blogs on all the intricacies of how to create these tracks. But I'm going to click on the track. I'm going to select the object I want the track to move. And then with my compass, I'm going to just slide this over to its ending location. And then I'll just come in here and hit the record button. The shortest distance between 2 points is a straight line, so that's what it's done here, right? It's beginning to end. So if I were to rewind this and kind of take a look at the path, and you can actually press play, you can see that once again, in CATIA, we are magicians. So notice my little ball here is just flying straight through those walls, no problem. So let me go ahead and set this back to the beginning, and let me show you here quickly. It's always, again, on you guys to do your due diligence, make sure there's no clash. But here is a button. These are what we call our clash detection. So you can actually turn the clash detection to stop the simulation dead in its tracks if it reaches or detects a clash. So let me zoom in here, and now let's replay it. And as soon as it hits this very first wall, again, it stops it here at 12 seconds. It says it can't go any further because it knows that it hit that solid object. So let me rewind this to the beginning and click OK. And now this is the whole beauty of the Pathfinder, right? So make this get from start to end, avoiding all of the solid obstacles, and have it CATIA to calculate it without me manually having to go through and figure out all those spots. To do this, we're going to find the Pathfinder button. And there's kind of a tiny box that pops up. It's wanting you to select the track that you want to find the Pathfinder for. And obviously it's pretty easy right now because I only have one track, but if you had more tracks, just make sure that you're being careful and you're selecting the right one. And all of a sudden we get our dialog box to pop up with those 6 surfaces that encompass the bounding box. So without making any adjustments, let's just see how CATIA figures out our mouse maze here. So if I hit apply, you can see that, well, that didn't take that long. It did find a path, but you probably can't tell that much from my camera angle. But if I rotate around, look what CATIA did. It said, oh, the easiest way is just to pop out of the maze and then go across. Well, obviously I didn't build like a top ceiling because I wanted us to be able to see it move through the maze. So that clearly shows us that we need to adjust this environment. And the way that I'm going to adjust this environment, I'm going to take the top surface and I'm just going to drag it down, and I'm watching for that yellow surface to kind of cut through the walls a little bit, just a little bit. So that says, okay, make sure it stays within the maze that I've created. Let's rerun that and see if it can make its way through the maze once again. All right, well, this time it once again, it kind of quote unquote cheated. It actually came out of the front and then went down. So I'm just gonna stop that prematurely here because I know that that's not what I wanted. So again, it shows you that you kind of have to make some more adjustments to your environment. I'm gonna take that front surface and just slide it in. So by adjusting the top and the front, I am confirming that this little mouse has to stay within the maze. With that, you're going to hit apply, and then we'll just kind of watch it. When it does kind of run into an obstacle, sometimes it bounces around a little bit. And then after it finds a path, it should move on. I don't know about you guys, but that's pretty impressive. I mean, if you think about how much calculation CATIA has to do right now. So you can see that through our maze, right, it still found its way around. It kind of bounced around in the first couple corners, but other than that, it kind of made its way around perfectly fine. And again, I'm not going to show you the different step sizes or the repulse effects, because once you start messing with those and hitting apply, that's where we're not waiting for like 20 seconds, we're waiting for like 2 to 3 minutes at a time. But again, see those comparative pictures in the slides, or I mean, if you want to make your own maze and give it a try yourself, you can see that it just takes a little bit longer. So I'm going to click OK, and then our track here in white is created. And let's play through this track again. So starting from the beginning, and I'm just going to zoom in. And I want you to notice that the little top protrusion, it's kind of tipping over a little bit, right? So it's not staying nice and upright. So let's grab this little slider bar here in the player toolbar. So instead of playing it, you can actually just kind of slide it to a certain location. And I'm just eyeballing this, but I'm going to say probably right around here. It's probably the most that it's tipping, right? So again, it started off with that little rectangular protrusion sitting nice and upwards. And now it's like way over to the sides. Again, that's going to be a bad thing if that little ball was filled with fluid and maybe it had an opening right on that little yellow surface. So I have a potential, spill hazard here. So I'm going to set my little mouse back to the beginning of his maze and just click OK. And then I'm going to hide that path. We're not going to use that path anymore. So to make sure that our little ball, our little mouse, stays nicely upright or mostly upright throughout the motion, we're going to first create a shuttle. And again, see my other videos for explicit details on the shuttle, but a shuttle is kind of just like a container where you can move multiple things at once, and it also allows you to set that vector field so that way it doesn't wobble. So I'm going to click on the shuttle, select my mouse, and then over to the Edit Shuttle dialog box, I'm going to say activate this validation angle, and with respect to the Z vector, which is going straight up and down, I'm going to say confine that to where it only allows it to rotate, let's say maybe 3 degrees. All right, so if it needs to wobble to move around an obstacle, it can, but it's very minimal. So I'll click OK. All right, my shuttle is now stored in the tree. It also creates a little symbol on the model. It kind of has a little axis system with the hand. I'm terribly OCD with my CATIA. I don't like stuff cluttering up my screen, so I'm going to hide that. And then now what we're going to do is we're going to create a track, but the track object isn't going to be the mouse. The track object is going to be the shuttle. So just like before, I'm going to click on the track. I'm going to grab the shuttle from my tree. I'm going to take my compass and slide it over here. Hit the record button. Straight line, start to finish. Once again, it would be flying through those walls, which is bad. So let's find a path around it with the Path Finder. Now this time you have to be careful because we do have now 2 tracks, right? The previous one, which is the one that we're not going to use. So just make sure you're clicking the right one, either from the tree, from the model, or from this box. And then once again, I got to make sure that I drop my environmental ceiling down a little bit, and then that front face, make sure it doesn't pop out the front of my maze. So just make those adjustments, and then let's hit apply. Again, it might bounce around some of these obstacles here, but it should find a path around it. Man, it really seems like it's getting hung up on that corner this time. But here's the thing, the major difference that you guys should be seeing now is that little yellow protrusion is basically staying upright the entire time. There we go. So it finally ends. And again, if I were to click OK and kind of play back through that, again, the biggest difference is by adding that shuttle, we kind of control that, what I like to call the wobble effect, right? We're controlling that rotational vector. So very minimal rotation there with respect to that Z-axis. So ta-da, here's our path. Now the path, it works, but it's got some imperfections. It kind of got hung up here in this corner. It's not like the smoothest path that I could create. So let's smooth that out. When we click on the smooth, we're going to tell it to smooth that track 14. And then you have to specify a translation step size once again. You can play with these numbers and see kind of what the little bit of difference it makes within the path. That translation step size I know is probably equivalent to like that medium step size. So it's going to not take super long to run here. So I'm just going to go with the default and click OK. And voila, here is our newly generated smooth Pathfinder track. Now the thing that you have to watch out here with the smooth operation is that sometimes it can reintroduce a clash. It also created the smooth with a polyline. So polyline's kind of like playing connect the dots, but you always connect the dots with just like a straight linear segment. So like notice the path is, you know, it's straight, 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 and I mean that's fine, but it's just maybe not as smooth as I would want it. So I'm going to come back into this track and just show you that part of the thing that you can do with the track is you have this interpolator where you can switch it from a linear track, again, a linear connection between all of those different, we call them shots, or you can come down to a spline. And obviously this spline would be like a nice smooth curve through all of these different shot points. But you definitely don't want to do spline because notice it gets really close to this wall. So it would definitely be interfering here and in probably a couple other locations. The one that I like is this one called composite spline. So what that does is it leaves the like the initial segment of your path, it leaves it unaffected, and then everywhere else it just kind of smooths out those connections, so no sharp edges anymore. So I personally think I'm going to go with the composite spline here. So I'll click OK, and you know it's still on you to do your due diligence to make sure that there's no clashes. So I'm going to come back to my track, make sure that my clash detection stop is activated. And then, you know, if you play through it, you just kind of want to watch it. And remember, if it does detect a clash, it'll stop it right away. So, you know, ideally you would kind of follow it along the whole path, making sure that it doesn't stop anywhere. And that would probably take me about another minute or so. So I'm just going to go ahead and assume that I don't have clash here. So I'm just going to go ahead and stop it a little bit prematurely. But again, you would want to make sure that you follow it all the way around. So I'll reset it back to the beginning. And now let's consider maybe having a minimum clearance distance that we want to maintain. All right, so we're going to jump back into the slides for a second, and we're going to talk about how to create what's called an experiment in our CATIA DMU fitting simulator. And then we'll come back into our maze example and talk about how to maintain that minimum clearance distance. So it is called an experiment, and this and that's what the button's called. And this enables you to analyze the results of some type of analysis. Usually that analysis is some type of distance or measurement or like a clash, but it allows you to analyze it at every step of the sequence. And this can be displayed in either tabular or graphical format. So the tabular format, it actually creates like an Excel sheet. And in the graphical format, it'll actually create automatically. So if you take a look here, they kind of had some parts and they were wanting to figure out a distance, and they wanted to check that distance throughout the time of the simulation. So again, if they were trying to prove, like in this plot, that they always had at least a minimum clearance distance of 25, right, they would be able to easily confirm that here with this chart. Now, this CATIA experiment does report what we call a sensor. A sensor would be like a distance or a measurement or a clash report. And those sensors must be included with a sequence. Okay, so the first thing that you're going to have to do is create the sensor, so actually run the measurement or the distance analysis. Then the second thing, so it's kind of not listed here, it's just something you have to know, you got to like make the sensor, and then you got to make it in a sequence. And again, I have a different blog video on like how to use those sequences and how to kind of put all of these things together. Like I want this part to move out first, and then this part to move out after that, and then these two other parts to move at the same time. So see that video on the sequencing. All right, second step is you're going to click on the button. Then you're going to select the sensors to be observed, and then you're going to hit apply. Now, when you hit apply, that actually runs the sequence while you are observing that distance, perhaps. It probably is going to take a little bit longer for that to run. So once again, have patience. Once that does run, you can then review your results. You can see the results in either the Excel sheet, or you can see it here if you click on to plot the sensors, you would see it in a graphical format. All right, so now that we know how to do the experiment, let's jump in back to our little mouse maze. So I'm going to click on the distance analysis here. So the distance analysis, there's a couple different types that you can do, but I want to do the minimum distance. So what I'm saying is find the absolute minimum distance between any spot on this mouse to any spot on this maze. So I'm going to switch this to between two selections, mouse and maze. And then I'll click apply. It kind of shows you a little preview. I'll go ahead and click OK. That stores it to the tree, distance.1. And right now in the initial location, there's a minimum distance, and it's actually from the floor of the maze up to here, and that's 5 mil. So we want to tell that distance to be recorded throughout this entire track. So to do this, you have to create a sequence. And then I'm going to tell track 14, which is the track that we see right here, to be added to the sequence. And then at the same time, I'm going to come over here to where it says Edit Analyses. I'm going to say, make sure that the distance value is analyzed as the sequence runs. Then you're going to click on the Experiment button, so Edit and Perform Experiment. You're going to select on your sequence. You're going to tell that minimal distance to be observed, and then you're going to click Apply. Now, when you click Apply, I'm just going to throw this onto my desktop and give it a meaningful descriptive name, so that way you can find the Excel sheet if you need to. But I'll just call this mouse to maze. And then once you hit save, just be patient because it's now going to run through. I don't want to move my mouse because while this calculation's running, you kind of want to let it just have its time. But as you can see, the little mouse, the little sphere is moving, and then you should be able to see that distance value updating. So for every single step that it moves along that path, it has to do like a quick analysis, figure out that distance. So again, this probably is going to take the longest for it to kind of chug along and move through. Please be patient with CATIA. Don't start randomly clicking when it's doing these analyses, because I don't know if any of you guys have ever run into this, but impatience in CATIA leads to a little box that pops up and it says click OK to terminate. And the only thing that you can do is you can click OK and it terminates your CATIA session. And basically you've lost everything until the last time that you've hit the save command. So patience is definitely required here when it comes to these items. So originally my maze that I built was about double the size, and then I realized that when I came to this in the webinar, it was going to take like 10 minutes. So I actually made it a little bit smaller. I made my maze a little bit smaller. Oh, and I don't know why it stopped here. We'll see. It seems like it's thinking. So again, just have patience with it. Oh. All right, guys, I don't know why, but CATIA decided to not take my little thing all the way to the end, and it stopped it right here. I'm not quite sure why it did that. I could probably get it to fix itself if I reran this, but that would probably eat another 3 more minutes or so. So I'll just run with it coming up here to this measurement. What you'll do is you'll click on the sensor and you'll say, hey, show me those results. So it's probably going to look something like this, where, throughout the time, it kind of calculates that minimal distance. So let's say that you had a requirement that said, I need to maintain at least a minimal distance of 1 millimeter. Well, that's a problem because we've got a minimum distance below 1 millimeter at just this one spot. Now there's a couple spots where it gets pretty doggone close, but this one spot probably should come back in here and fix that. So I'm just going to kind of eyeball this location. It kind of tells you the reading down here, but it's about 255, somewhere in through here. So now that we know that location is kind of the problem child, let's go fix it. So let's click OK. Let's come back into this track and let's kind of slide this around to about that 250 location. So it looks like it's having the most problem right around here in this corner. Okay, so what we would like to do is kind of adjust this path. So even if you've made a path with the Pathfinder and you've smoothed it, you can always come back in here and adjust these. And it's pretty easy. So double click on your track, and then in the track player, you want to drop this down to the shot. So that, again, look at those other blogs. You kind of develop the track by like moving it and then hitting record, and that's a shot. Moving it again and hitting record, that's a shot. So I'm going to say, okay, go to the shot, which is shot number 12, and then I'm going to kind of move this out, maybe like to here. And then there's a modify command. So y'all, hopefully everyone saw that the path kind of moved away from that a little bit. So by me physically moving the location of it over, right, I've then told it to have a little bit more space to kind of work around that. So that should, you know, fix my 1 millimeter clearance. And if I wanted to, you know, double check that, I'm just gonna play through it here just a little bit. Like if I wanted to double check that, like I would have to go through the exact process that I just went through. So make another experiment and let that run and let that chug for like 3 or 4 minutes here. So I'm just gonna play or pause that and kind of bring it back to the beginning. So assume, because I'm almost here at the end of my hour, so assume that I reran that experiment and now that little spot, right, is good. And everywhere on this curve, we kind of have that 1 mil clearance. I wanted to leave you with one extra little quick visual tool, which is really handy, and that's the swept volume. Swept volume is also available in the kinematics area, but the swept volume creates basically a CGR quality object that shows you all of the space that that part occupies throughout the motion. So when you click on the swept volume and wait patiently for the box, you're going to tell it the track that you want it to basically be created for. So mine's track 14, and then make sure that you are highlighting the proper part. So I'm going to make sure that it's doing it for the mouse. So then at that point, you just hit save. And I'm going to just throw this here onto my desktop, and we'll call this mouse.1 underscore swept volume is fine. I'll save that. Then we can close it. And the cool thing is you can actually drop that back into your environment. So if I right click and do the component, existing component, and grab that mouse swept volume. Oh, all right, did not drop it in. Let me create that swept volume once more. I don't know, didn't pop up. Okay, so let's make this mouse.2 swept volume. All right, so I've got my little preview here of the path that it should follow. And we'll close that out. Let's try and drop that back in again. There we go. I don't know what happened that first time. So what I like to do is I like to take that swept volume and make it a little bit see-through. And so now you can actually, if you wanted to, you could probably come in here and just do like a quick visual inspection to make sure that everything's fine. So this is the actual like physical space. It's in CGR quality, but it's the physical space that this mouse is going to occupy throughout the entire track. So if I come back into the track and then hit play, like you'll notice it's staying within that amount. I don't know. I always think that the swept volume is kind of a neat little visual tool to have. And then the other thing that you can do with swept volume, I'm just going to go ahead and stop this here. The other thing that you can do with the swept volume is you can measure. So if I want to, you know, I would say, hey, I want to measure from the swept volume to the maze. And now you can see that, you know, I made a little tiny mistake. And that mistake was, you know, remember this corner, I like adjusted that corner to kind of back it away. So that way I had that minimum clearance. Well, by adjusting that corner, I kind of modified the spline somewhere else. So now I actually have a minimum clearance distance that's being, you know, violated here. So again, you would have discovered that if you would have reran the experiment, or now you can quickly discover that with the swept volume. And once again, you could come back in here to this location and probably take this spot and like move it up a little bit higher. But again, this tool, this Pathfinder, is going to be your best bet when it comes to like, I need to find a way of assembling or disassembling this and showing it, right? But I don't want to have to manually like move it and hit record, move it and hit record over and over again. So Pathfinder, definitely a really nifty tool to have when you're using that fitting simulator inside of CATIA. Then let me kind of jump back into our slides here and finish this up. If you are watching this webinar and you've never done fitting simulator, you've never done CATIA, if you just need a refresher on all this, you know, education is so important, because these software systems that you guys are paying kind of ridiculous amounts of money for, there's so much that's underneath of the surface that you may not ever really know that it's there unless you take kind of an education, a more structured education class. So you're going to have this structured learning environment with our classes, you know, taught by certified instructors. All of our classes we can offer practically online. So, you know, stay safe, stay home, and still learn. And then here I've included just a chart of all of the CATIA classes that we offer and 3D experience classes. I've highlighted the DMU fitting simulator. Everything that I've covered today, tracks, sequences, detecting clash, Pathfinder, that's all covered in the fitting simulator class. And it's only about a 4-hour class. So it's, you know, if you're thinking about maybe contacting us to offer this to your employees, it's not that much of a time requirement that you would be pulling them out of their job, normal job functions. So feel free to reach out. And then at this point, I'll hand it back over to Corrine.